much all the time scales all at once. Okay, did my screen go away? No, we're still good. Okay, great. Okay, so what are the main controls on Arizona climate? So I break it into these parts. So the first thing we'll talk about is topoclimate and seasonality and precipitation. So we have a seasonal transitional climate. So we have monsoon versus winter storms. We have two different seasons, which become important in delivering precipitation at different times of the year with these breaks in between. And so you end up getting fairly complex soil water balances at shallow depths to deep depths. And you also have this element of cooler, snow-driven, typically at higher elevations during the winter time, low evapotranspiration type precipitation during the winter time, which leads to typically deeper infiltration. And then the monsoon's quite different. It's usually convective, highly isolated, very heavy, lots of runoff, but it can also put deep plumes of water in by the end of the season. But it also is occurring in an environment with a lot of evapotranspiration. So the water balance isn't quite the same. Okay, so that's kind of the topoclimate and seasonality aspect. Then we also have El Nino southern oscillations, so over longer periods of time, and decadal variability, and we'll talk a little bit about this, is the variability that we'll see on the order of decades, long-term drought and wet periods. And then climate change, which is occurring with all of these elements together, warming temperatures, shifts in the hydroclimate from snow to rain, and increasing evapotranspiration. So these are kind of all the elements we need to try to piece together to understand climate down here in Arizona. Okay, so I would start off with, I'm just going to do a couple of kind of quick run-throughs of sort of physical geography. Everybody's, I'm sure, really clear on this, but I always think it's kind of nice to just remind us that we have really interesting geographic features, physical features of the region that give us an interesting climate. And so this is just, it's a gridded long-term average temperature map, and it really is just a rescaled topographic map. And so we can take station data, we can interpolate it, statistically regress it against elevation and get nice long-term climate averages at different elevations because temperature follows elevational gradients really nicely, just the way the atmosphere works. And on here you see these are watersheds. These are sort of smaller watersheds here in Arizona, mapped on here, and you can see that the watersheds break at the higher elevations and then they flow down to the lower elevations. So here in the state, it's no mistake that we generate surplus water at higher elevations and it runs downhill to the drier parts. And that is an important part of the sort of type of topoclimatic variability temperature-wise across Arizona. Okay, and so one thing I was pointing out here too is that if you were to take a map from back east that's flat, it'd be one color. So we know this by looking at the vegetation. You were just talking about Sky Islands earlier, is that we do have these gradients in elevation, which drive really different water balances, temperatures, and different climates from higher elevations to lower elevations. Precipitation is similar, but not quite. It doesn't quite follow elevation. It does really quite closely. Higher elevations can induce precipitation as storm systems go across the Mogollon Rim. That rising air being pushed up causes a maximum precipitation right along the rim. Descending air on the other side on the northeast part of the state is warming and drying, so it dries out. So it's a high cool desert versus the low desert, which is away from moisture and elevational sources that would induce that precipitation, so it's dry there. We have the Sky Islands, the Mogollon Rim, and then up to the northern part of the Colorado Plateau, higher elevation, which can in the wintertime induce that precipitation, but also in the summertime, higher elevations become a focus for convection. So those mountains sticking up in and collecting that early morning sun, and they have that moisture typically, will generate clouds first, and you'll have more rain earlier at higher elevations than you will at the lower elevations. So that kind of elevational precipitation relationship holds here. So again, so that we've got this steep gradients in precipitation, we can look just out the window and look at the Catalinas and see that vegetation giving us that long-term integration of topoclimate. We see it here on these sort of comparison maps, and being the plant society, you're real familiar with the biomes, and I always like to try to sort of draw people's attention to all of the Arizona biomes on that upper right map, which is even, you know, a coarsification of the real diversity at smaller scales. But one thing I find really interesting when we start to pivot towards this topic of seasonality is that the far northwestern part of the state, low desert, is Mojave Desert, the central part of the state is Sonoran, and the far southeast part is moving into Chihuahuan Desert. So we have this sort of collision of these three deserts occurring across Arizona. And one of the big predominant differences between them is the seasonality of the precipitation. So Mojave Desert, more wintertime, Mediterranean climate, think of California. Sonoran Desert is both summer and winter, and Chihuahuan is slightly more summer. And so having that, just that diversity of the timing of precip leads to some of the biological diversity we see across the state. And I think it's important also to try to get a handle on that when we think about climate change in the future. All right, and so this is a map here, and I'll just try to walk you through it. And it's got a lot going on this. I'm gonna even forward it here to look at some of the different impacts, or sort of the reason from I'll give this talk to resource managers, is thinking about precipitation seasonality. This is a cookie cut out of Arizona. So taking gridded data, it goes back to, again, there are statistical estimates for the whole state. So it's taking the wettest and driest states, and we're gonna average them all out, come up with one value for every month going back to the early 1900s. So it's kind of an abstraction of individual locations of climate, but it gives us a sense of, through the annual cycle, when is the precip occurring and when isn't it? And so it starts in October. I've got the scale to the water year on the far left. The black line is the median. So it's the middle value of the 120 years, 120 months, 120 years of, and for that particular month that looks at that distribution of values. And so you get these little blue areas on the top and bottom there, and that just shows you the shape of the distribution. And so that black line, we can follow it along here. It's, you know, it's 0.75, which is kind of meaningless for any particular location, but it gives us that sense for Arizona. We move it across, and it starts to picks up in peaks in December. It's a little noisy. The January drops a little bit, but you could think of December, January, and February as being high. It starts to decrease in March, drops off in April, and we move into that seasonally dry springtime. April, May, June. June is often our driest month, but sometimes it isn't. And so the median is the lowest, but it also has a slightly higher bit of variability because we can have the monsoon moisture coming in early, and it can be quite wet in the very, very tail end of June, but often is very dry. And then we move into the monsoons. So there's a real strong rise in seasonality precipitation here. So July peaking in August and dropping back off. So we have these distinct seasons of the cool, wet, I use it air quotes, wet winter, dry spring, monsoon, and then the fall is kind of a mess. The October, if you notice here, it's got this huge blue band here. And if you've lived here for a while, you know October is mostly dry until it isn't. And it's usually a tropical storm. Or, you know, we've had October 2000 was one of the wettest Octobers Arizona has seen. And it was kind of a strange wintry type storm system. So it's got opportunity, but often is dry. So we've got this sort of pulsing of precipitation. And that's important because it puts water into the soil, the vegetation and ecosystems respond to that and are adapted to that largely. And so the coming and going of the precipitation is important for a lot of our ecosystems. Okay, and so this is really similar. And so these bar graphs are long-term average monthly values for these regions here. They look like counties, and it's pretty close. They're actually called climate divisions, which is just groups of counties. And you can go up here in the far northwest here, which is, I think it's just Mojave County. I don't think La Paz is grouped in there, but these bars here, the first bar is January, February, March, and it goes all the way through December. And it's just a little thumbprint, basically, of the seasonality of the climate for these different parts of the state. So you can kind of scan across this map, and you'll see that the far northern part of the state has a little bit higher bars in the winter and a little bit shorter bars in the summer. You go down to the southeast, is that real contrast. It's got decent bars in the winter, but much, much higher bars in the summer. And that's what we were talking about earlier, is that as you go farther to the northwest, the monsoon signal drops off, but the winter signal picks up. And as you go further to the southeast, the monsoon signal picks up and the winter drops off because you're getting more into the Chihuahuan Desert. Kind of in the middle along the Mogollon Rim, it's kind of high in both because you're getting the elevational aspect that's helping with that precipitation. And then if you look at April, May, and June, especially May and June, pretty much dry everywhere. It's rare for us, for any part of the state, to get much precipitation in those 2 months. And so we're in the middle of May right now, and you've been noticing there's not much going on, and there typically isn't. It's not impossible for it to rain in May. It did a couple years ago, May of 2019. We had a beautiful, cool May and a decent precip event right in the middle of the month. It was very, very unusual in the historical record, but it can happen. But on average, it's typically that transition month between the winter and the summer as we're moving into the monsoon season. Okay, and so then finally, so that was you're keeping score, topoclimate, seasonality, and then we'll finally talk just quickly about ENSO. And so the longer term variability, which I'll show you in some plots coming up here, is related to changes in the sea surface temperatures across the Pacific Ocean with some regularity. I wish it was more regular, it'd be more forecastable. 3 to 7 years, sort of cycling between El Nino and La Nina events to neutral. So when you have an El Nino event in the winter time, it tends to enhance the subtropical jet and steer storms across the Southwest and give us wetter than average winters. And La Nina's, it's not quite the opposite, but it's a disruption to the jet stream, and it basically shoves the mid-latitude jet up through the Pacific Northwest and steers. We don't get a ton of storms in the winter anyways, and so if you take a couple of them off the table, you end up with a dry winter, and that's certainly what you see in La Nina winters. And you may have guessed, or you may have known, that this past winter was a pretty decent La Nina event that formed last fall, strengthened to about moderate status, and is just now starting to release us, but it's too late at this point. And so we'll just have to kind of see what neutral conditions give us for the summer. Okay, I'm going to skip that. All right, so longer term variability and change. And so we're going to look at now some plots of variability at different parts of Arizona. And I'm going to first start with this tree ring reconstruction of wintertime precipitation for Southeast Arizona. So this is produced by the Tree Ring Lab on campus. And then we serve it up as some figures through the climate assessment for the Southwest, which I'm part of. And this is basically taking tree ring cores from trees across Southeast Arizona, and then calibrating the ring widths against instrumental precipitation records for this region. And then you can use that statistical relationship to look at rings prior to the instrumental record and then get an estimate of what the precipitation in the wintertime was prior to the instrumental record. Okay, so this is 1000 AD. I believe this one ends in 1988 appreciate that one. This one ends in 1988. And it is showing us November through April precipitation percent of average. So the black line is 100%. So in a given winter, if it falls on that, it's just the average for the wintertime precip. And then 50 is half, 50% of average would be half, and then 150 is 1.5 times the average. So you can see here, if, looking at Southeast Arizona climate variability, and we know this in the literature, it's in tons and tons of papers. There's lots of climate variability, and there are some very strong, deep drought signals in the past here, in the 1600s and the early 1100s, and then there was one in the late 1800s. And so some of the more contemporary droughts we've seen here aren't even quite as bad as the ones that we've seen in the reconstructed past, basically in the dendroclimatological reconstructions. And so I think that's really important. And this has been really important work for water managers who've really started to take a look at this. When water managers were using just 100 years of data on the Colorado River, or even shorter, they didn't have a full understanding of what the climate variability looked like here in the Southwest. So these tree ring reconstructions have really been really helpful for us to understand that even recent droughts, they're not as bad as the ones that have plagued the Southwest in the deeper past and say the last 1,000 years. And so that's kind of important for us to keep in mind when we suffered through it was the driest summer on record this last summer. But I was talking to a colleague who's got access to all of these tree ring reconstructions for summer precipitation here, and he says, oh no, that last summer wasn't the worst, and it certainly wasn't the first time that we've had a failure of the monsoon. So that's both kind of terrifying and encouraging at the same time that it's not necessarily a new climate change signal emerging. I don't think at this point, but it is, you know, it's sobering that we do live in a place that can get very dry very, very quickly. Okay, and so we'll look at the last 100 years here. And so now I'm going back to Arizona, cookie cut out the state. I'm using that gridded data, and then I'm getting a January through December total precipitation. So total average precipitation for the state. Remember, it's the wettest and driest, just that average number. And it goes from 1900 and it ends through the December of 2020. So it's just through the end of the last calendar year. And I'll bring it up to date here in a couple of slides here. Okay, so we can look here, the black line is the long-term average, and this orange line is a moving average. I believe I put a 5 or 10-year moving average on this. And just so we can see from year to year, we do a lot of sort of careening back and forth across the average, very rarely hitting the average on the nose. And we have a lot of variability in total precipitation here on an annual basis. And you can see here that we've got decades where we hang on average and a moving average hang above the average. And then we've got decades where we're below, we're above, and we're below. So this is that concept of decadal variability. And it's largely attributed to changes in the El Nino Southern Oscillation and ENSO variability. So cycles in the Pacific Ocean, in the sea surface temperatures in the Pacific Ocean that sort of cluster in time over decades, that give us runs of wet winters versus runs of dry winters. And so that can then stack up and give you longer term drought periods. And so more recently, you can see that we went from a very, very wet period in the 80s, which I think has raised a lot of people's expectations for Arizona being a wet place, and it's not. This is unusually wet when we look at any sort of records. And we've been sliding down more recently because of decadal variability. So sort of a shift from more El Nino events in the 80s to more La Nina events in the most recent decades. And there's an interesting thing here too, that, you know, when we think about decadal variability and precipitation in particular here in Arizona, this is what we've seen in the deep past. And it's also what we see in the models going forward, is that this variability continues. So this tailing down here, I really thought we were turning a corner here, and maybe we might still be. It's hard to know at this point. And the problem is you don't know until you're many decades into the current cycle. You can look backwards and say, oh yeah, we're in that thing. You don't know in real time. But it's hard to remember. We've had a couple of bad drought years, but we actually had we've had several decent winters. And it wasn't too long ago, we had a couple of good summers too. So we were putting together some decent precipitation amounts over time. But then we've had, and I don't want to downplay it, but we did have 2017, 2018 drought, which was a really acute winter drought. And then we had the monsoon really faltered in 2019. But as Jack mentioned earlier, we had a decent winter last, it's hard to remember, in 2019 into early 2020. But then this monsoon failure so spectacularly really has pulled the precip down. So that's where you see the failing of the monsoon is really what constructed this almost record dry total relative to 1956. So they're almost neck and neck here. Okay, so we can rescale this, and we can this is a drought index, the same values going forward here. 1956 on this particular estimate here actually just edges out 2020 on the calendar year for being the driest year on record. And you can carve it up in different ways and look at different locations where 2020 was drier than 1956. But this particular data set, it's pretty much neck and neck. And so you can see here the red bars are those runs of dry years, blue bars are runs of wet years, and then this is a more recent drought. And that black line, the 10-year moving average was flipping up a little bit, but I think I got faked out by that. I was way too optimistic. I don't know. I'm kind of eternally optimistic, so I'm still hoping that that's the challenge. The problem is that it's getting warmer, and that is really, it's eating away at any gains that we get with a sort of a reversal in drought conditions. And this is the thing that we're kind of struggling with from a research standpoint too, in the area I work on, sort of drought monitoring and thinking about soil moisture is, and I'll show you in a couple of slides here, is that with warming temperatures, there's higher evapotranspiration. So this is the temperature, annual average temperature for Arizona from this particular metric. In 2020 was the warmest on record, beat out many of the earlier years by quite a bit. And then if you can combine these two things, as I mentioned, one of the drought indices we look at is standardized precipitation minus evapotranspiration. So thinking about a water balance, this is pretty coarse though, and I think we need to do better than this. But it does have the combined effect of dry conditions and warmer. This drought index just fell through the floor. 1956 wasn't even close drought intensity wise because it was so much warmer, even with kind of comparable deficits in precipitation. So that driving more water out of the atmosphere, and the plants know this, and that's why I think the plants really struggled with this particular year. Okay, and so there's some really nice maps on the Westwide Drought Tracker that I pulled together here. This is the 12-month drought index through December of 2020. And so red is never good on a climate map, and you can kind of use that as a rule of thumb, and brown too. Those are two bad colors. Greens and blues are typically what you're looking for on anything kind of climate related. And this is very dry, record dry, that deepest dark red color for the 12 months here. This is temperature here, so it's record warm, record dry. The combined effect is record low standardized precipitation minus evapotranspiration index. So just hit the floor on drought conditions in the instrumental record. Okay. All right, so, and this is fairly obvious, but this is kind of where the state of the science is right now on thinking about drought here in the Southwest. The warming temperatures can shift the average soil water balance. Increasing temps, increase potential evapotranspiration leads to increasing aridity. And so there's been a lot of, the media reporting has been a little frustrating on drought down here, because I think we're conflating concepts where the term mega drought I don't find particularly helpful, because it comes out of literature from tree ring analysis where we found really long duration deep droughts in the past. And I think it's useful for describing that. But when we start to kind of use it to describe very intense short-term droughts, it loses its effectiveness. And it also becomes complicated when we're talking about drought intensity changing because it's getting warmer. And that's actually a shift in aridity. It's not necessarily drought, because droughts by definition end. And if temps are getting warmer and it's shifting water balance towards more arid conditions, the drought will never end at that point. And so it becomes a meaningless concept. So I think we just have to be more careful with how we talk about these things. So increasing aridity is really what we're talking about here, and on average over time. So we can still have wet years, wet seasons, improvements in soil moisture, and plants that are really well adapted can take advantage of that. But it's the on average over time is that things that need certain conditions will start to suffer because they're integrating over longer periods. And it's also the kind of precip matters, snow versus rain, when, how much, and often and how much. So I've been really interested in sort of thinking about the timing of precipitation in relation to soil water balances here. Okay, so here's a kind of a quick look at another maybe overly, unnecessarily overly complicated plot. But basically it's dropping a pin in on Tucson, and then it looks at the total precipitation from December through January for all the years between 1979 and through 2020. And so the y-axis is precipitation and the x-axis is potential evapotranspiration. And so what I think is useful about this particular plot is that they do align along an axis here. And that's important to remember, is that dry years are typically warm years with higher evapotranspiration, and wet years are typically cool years with lower evapotranspiration. That's in water limited systems, that's a feature of the climates in those areas. And so what I think is important about this is that we've certainly seen a shift. These red dots are all later decades, and it's on the warmer, dry, but it's on the warmer, more drying, and it's on the lower. What I expect is, and I don't know when, is that future decades, we will have a decade that's probably on average wetter than the longer term average, but it'll be warmer. So we'll be in this kind of upper right quadrant. And it doesn't then mean that the same amount of precipitation has the same sort of effectiveness with you know, all of the things that are important to us here, recharging water resources, soil water balances, and those kinds of things. So that to me is kind of the outstanding issue here, is thinking about when we do have wet years, how effective is the precipitation? Is it something about the timing? Is it something about that particular year wasn't quite as warm? When we do have warm years that are also wet, is that, what's an analog in the past for that? So I'm kind of interested in that kind of conceptually. Okay, so we're gonna move forward here, do a kind of a quick recap on the last 12 months, and then we'll move into the climate projections here. All right, so this is May through April precipitation. So this is the last 12 months, and it doesn't look a lot different than the previous maps I showed you, because it really isn't. This actually moves the, if we think about if anybody can remember last May, this felt like it's been 10 years in one, but last May was it got very, very warm. The end of April, it got very, very warm, and May got very, very warm. And we were kind of on the cusp of the monsoon. And so we've got a very warm, dry period through April. And so that collectively has the failed monsoon in the middle of it, and then this really mediocre, poor performing winter in there. And so it leaves us with record dry conditions in May through April, which I was concerned about in the fall because we had a La Nina on deck, and the La Nina didn't really, it did what it promised to do, which was not much. And here we are with that. So precip very dry, and then the temperature here, which is interesting, is that we had a record warm summer. We've actually had a mild winter in spring, and that kind of like dragged down the epic hot we have here. So it's still the top 10 percentile, but this map would be much, much redder as far as record conditions if we would have seen the warm temperatures, and we did. We had a lot of moderation from cool systems kind of coming through the whole winter time here. Okay, and so I make these crazy plots because I'm a climate nerd, and this is Tucson data for October of 2019 through September 30th of 2020, and it just takes the daily precip and temp and it plots it out here. But it's just kind of draw your attention to this cumulative precipitation plot here. So it's hard to remember, but we had 2 winters in a row where we actually had good fall precipitation, and we had good spring blooms, basically, because we had these 2 years in a row. And so just going back here, it's hard to remember, but we actually had a really quite splendid winter time here with very wet. These are little orange dots, are record daily precipitation totals in November of 2019. And then the spacing of the precipitation was frequent, decent amounts all the way through March and a little bit into April, and then we're done. And then it got hot, and that's where this bottom plot here is. All these little red diamonds here are record highs. And the monsoon, which should have started tracking up in July, all that brown area emerges because it didn't keep pace. And so for the water year, we end up below average. But we had this really nice kind of cushion early on. So just, you know, it makes me think of looking at some of these training records. There are multi-season droughts that are much, much worse than we've seen this past year, which is really kind of scary. But maybe that's the upside here, is it could have been a lot worse. It was bad, but it could have been a lot worse than it's been in the past, except for these warm temperatures on top of it. Okay, and so then I'm going to zoom here, and this is now October 1st of 2020. So it's through the beginning of our current water year, and it's just running out to, and this plot was updated yesterday. And so you can see here that there's a ton of brown area in here. It means that our cumulative total precipitation has not come anywhere close to matching the average rate here. But I draw your attention to the little stair steps here are they're pretty evenly distributed, so that we haven't had super long dry stretches. And again, I feel like I'm kind of like shining a turd here because it was a terrible year, but the spacing of these precip events, and then getting one in March, which again wasn't much, and even a little bit of snow we had in late January, is better than I thought we were going to do, if you can believe it or not. You know, 2017, 2018 was much, much worse as far as the way a La Nina could have played out, and it was better than that. The interesting thing is this little graph in the upper left corner here, it's got these analog years, and it's interesting, 2011 is actually an analog for current conditions. And so if anybody remembers 2011. It was a very dry year. It was the beginning of the terrible drought in New Mexico and Texas, and we were kind of on the far western edge of it. And it was also the spring of the Wallow fire that burned up in the Mogollon Rim. So we're not in good company as far as precipitation, but we've had drier winters in the past. Okay, and so finally, to abuse you with some more crazy graphics, this is another graph that I put together, and what this is it's taking monthly total monthly precipitation, and this is for all of Arizona again. And so the bars plots at the bottom here are whether or not that particular month was above or below average. And so you can kind of look at it across there. You can see the bars sticking up are wider than average, and the brown bars below the zero line are below average. And what I do is I take a drought index and I calculate it at 1 month, 2 months, 3 months, 4 months, and I just use this moving window that grows over time. So the y-axis here is a growing time scale. So you move that window across this whole data set. And so what you can do is you can find those periods that are hanging together as wetter than average or drier than average. And so the reason I use this is that we can have short-term high variability in precipitation, which is at the bottom of this graph here, where you can see those little tiny stripes. And those are wet periods where you could see recovery of things briefly. And if they grow into longer periods, because you're getting more of these clusters of wet years together, you get longer term improvement. But you can see the 80s here, we just kind of rained all the time. We had these really nice, it was kind of wet at both short and long time scales. And it was in the late 90s, really precipitated by the 2001, 2002 drought, very, very dry conditions and a long stretch of it. And then as you get to about 2013, though, you might notice that there's more green showing up, and you start to see these kind of white colors, which is average at the longer time scales. That was the little flip up that I thought we were turning a bend here. And then this is the more recent, very deep drought conditions that show up. One of the darker colors you see in the whole plot here from the last 12 months. Very, very. So it'll be really interesting to see what happens for the summer and then next winter and the following summer to see if we start to pull out of this. But we'll have to kind of turn our attention to what the outlooks look like. So that was my pivot to, this is the El Nino Southern Oscillation Outlook that was just issued today. So this is the May 13th update. And so what this is it's giving us a probability in these 3-month windows going forward, what the most likely outcome is, whether or not we're going to be in a La Nina, neutral, or El Nino. And so currently, there's like no chance of an El Nino popping out of nowhere. That's would be useless at this point, quite honestly. But the gray bar shoots way up, and that's the short-term forecast is, and we already see this. The Pacific is relaxing; it's going back to neutral conditions. Temperatures are average across the equatorial Pacific. And then as we get through the summer, that's still the most likely outcome at this point is ENSO neutral for the summertime. And then the outlook today and the discussion is that there's growing concern of a double dip La Nina, which would be a second winter in a row of La Nina conditions. And this is disconcerting. It's very common in the historical record. 2011 was a double dip, was the beginning of a double dip. It actually reemerged in 2012. And so that leads to back-to-back dry winters for the Southwest. It's not a done deal. This current month is the hardest month to make an ENSO prediction for the following winter because the whole Pacific Ocean is reorganizing seasonally. So this is just, we shouldn't sweat it yet, but it's something to keep an eye on, that even with a good monsoon, we may be looking at another below average winter coming up. So much for my idea that we were pulling out of a longer term dry cycle. Okay, so these are the outlooks from the Climate Prediction Center. And this is interesting. This was issued in on April 15th. So it's just about a month old, and the new update will come out next Thursday. And I'm really, really interested to see what it looks like, because in April, the Climate Prediction Center started to paint green on southern Arizona. And I don't know if they knew what they were doing, and as far as don't mess with Tucsonans and our monsoon forecasts, because I'm a little worried that this may have been just too optimistic of a forecast at this point. It is it's great to see green on the map. The introduction of the this probability anomaly, and all it is it's basically saying that there's a slightly increased chance of seeing on the total precipitation for the monsoon season will be above average. Doesn't say how much or where in particular, but the whole sort of region has a higher than average chance of seeing slightly higher than average chance of seeing above average precipitation. The dynamical forecast models are not very good with the monsoon this far out, and they've really been waffling. I looked at the recent one today from the European Center, which is very, very good, and it's kind of, it shrugs basically and doesn't say wet or dry, which I think is encouraging because it's not a strong dry signal. So I'll take that at this point. I'm really curious though if Climate Prediction Center is going to stick with this forecast because they're seeing something that that I'm not seeing on some of the models. So stay tuned and hit your refresh button next Thursday to see the new models come out, and hopefully this increased chance of above average will still be there, and we can. It's not going to be a strong, high confidence forecast though, and so we have to steel ourselves for this to not be the eventual outcome. Okay, and then the temp outlooks are kind of boring because they're always above average. This is temperature trend. This is the climate change signal coming out in your seasonal temperature outlooks. Everybody saw that the normals have been updated. That was big on the news this last couple of weeks. These maps are still using the 1981 through 2010 normals. Once they move forward, you won't see as much red on these maps because the whole average will have gone up, and it'll be harder to make a forecast of above average because the whole average is now higher than it was in previous decades. So stay tuned on that. Okay, so I'm just gonna kind of quickly move through some of these climate projections here. And I'll just start off with this sort of quick kind of overview of the idea of why do we use climate models. And it's basically, we can use them for two different things. We can use them experimentally for attribution, and we can use them to make projections. And we do them for both. But some of the first work with climate models is for attribution. So it's how do you know that greenhouse gases are changing temperature? Well, the only way that we don't do field experiments with the planet. We don't have a control planet. So we have to use a model. We have to build a control planet mathematically. And so this is an old study. It's used over and over again as a sort of demonstration of this. But basically, if you take an actual instrumental temperature record, the average for the planet, the black line, and you run a climate model with just natural variability, volcanoes and solar variability, you get the blue line. And then if you run a model where you add in anthropogenic changes, greenhouse gases and sulfates, you get the red line. And so just sort of matching those two up to see the changes observationally in the black line at the end of the record, you actually have to have the anthropogenic change. So that's the attribution part of this. So that's part of the whole process of doing climate science. Okay, and then on the side of using climate models, this is where kind of in the whole spectrum of weather and climate products we use weather forecasts issued by the Weather Service here in the US, which are numerical models that are completely constrained and befuddled by natural variability in the climate system. So just where are the highs and lows, and what are all the changes in the energy balance at very, very short time scale. So that's sort of internal variability. To get out to seasonal time scales, it's ENSO. So like El Nino Southern Oscillation, slow moving variability in the oceans. It's not until you get out to longer time scales that you actually see the climate models really pick up on what they do well, which is differences and outcomes between greenhouse gas forcing. So that's the difference between internal variability, which is sort of short-term weather and climate, and are just not having all of that information dialed in as a scientific uncertainty. Further out in the record, the uncertainty in the greenhouse gas forcing starts to cause separation in those. So that's kind of the key point I want to make here when I talk about different emission scenarios. And so emission scenarios, this is actually an older graphic, and there are new emission scenarios out. This is, I think that we're on the third or fourth iteration of these. But basically, emission scenarios are looking at projected changes in greenhouse gases into the future. And so that's not a purely physical projection. It has everything to do with geopolitics and energy policy and technology, and physical feedbacks within the planet. So you have to have all these really sort of creative teams to come up with possible future emission scenarios, and then those get plugged into climate models. You look at end of century to see where you get separation in local climate variables on that. So we'll talk a little bit more about that. But basically, some of these emission scenarios, this is the last version of it, is had a very high emission scenario, which is radiative concentration pathway 8.5. So that's 8.5 watts per meter squared, extra watts per meter squared over the whole planet. It's a lot because of greenhouse gases radiating that back to the surface. And then a smaller one, which is quite optimistic, of only 2.6 into the future here. So you get this range. You can see one is very optimistic, one is very pessimistic, and then we have a lot of room in the middle here. Okay, so this is really quite interesting because this came out, this is a paper in Nature from last year. And when we have all these emission scenarios, this is now trying to reassess within our emission scenarios, what are the most likely paths here. So the 8.5 path here, which is used as the worst case scenario, is based on this assessment, highly unlikely. And it's a worst case no policy, which is highly unlikely because we have policy in place. It's not great, it's not fast enough, all those sort of caveats, but it really does make this worst case highly unlikely. So this is average no policy, this is unlikely. We'd actually have to go backwards to get to this outcome. And so we're kind of down here, which is it's called weak mitigation right now. Puts us at about a 3°C rise, which is too much. And then modest mitigation is about 2.5. And then the mitigation required to meet the Paris goals is down here at 1.5. So we're kind of down here. And I just want to give you that context because I'm going to show you a couple of projections that are really on the outer edge of these scenarios, and they're probably unlikely. I just want to give you that caveat. And again, these projections are not forecasts. They give us some understanding of changes in local climate based on our understanding of how climate works within these climate models. Okay, so I'm going to pull data from this really handy tool you can play with, very easy to use, climatetoolbox.org. And you can drop a pin, and then you can get a lot of different variables scaled to local climate. And so this is, top one is RCP 4.5, which is, it may be a little more, we're kind of in somewhere between 3 and 7 is probably that's probably even a little bit high. So it's probably 3 to 5. So this is on the lower emissions side, and then the higher emissions. And again, useful to know if we have unknown feedbacks, permafrost and methane belching and sort of unknown things, which are right now thought to be unlikely, but if they do, you could have this, unlikely outcome. But it gives us a sense here in Tucson what these different outcomes look like. And so you can look across here and look at average highs and lows, and then the hottest days. In the lower emission scenario, it goes from hottest days in Arizona of around 110. We've already saw, we've seen 110 to 115 here. That becomes more normal and more frequent under this lower emission scenario. And then in the higher emission scenario, you can just add 5 degrees to all of these things. It's just that many more degrees on top of it, which is a lot on average by end of century here. So it just kind of gives us this landscape of possible outcomes here to try to understand changes here. Okay, and so then I think it's useful to sort of plot these together. And the mean temperature is kind of what you expect. They both go up. The higher emission scenario goes up more and faster than the lower emission scenario, and they all sort of end up several degrees above current climate. So that's fairly obvious. Okay, what I think is interesting though is on the precip side, is that precipitation projections for the Southwest are notoriously hard to do, and they have very little agreement with each other. And so this is the historic, gives you that same sense of that one of those first plots I showed you, which we just have lots of variability in certain months, right, around the median. And this just gives you a sense that even on an annual basis, that green bar plot I showed you there, we have lots of variability. And so that is our historic, and that continues into the future. So we have lots of hydroclimatic variability. El Nino Southern Oscillation, we don't have a good handle on it in the climate models. but it still shows up. It doesn't ever go away. It has some shifts in frequency, maybe becoming stronger, maybe swinging more wildly, but either way, it gives us similar climate variability that we've seen in the past, but it's occurring under warmer conditions. And so between the two emission scenarios, the variability is about the same and the change is net zero because it's kind of a flat line. So none of them suggest that we get drier, we get warmer. And that's the two things to sort of work out together. I'm gonna skip that one. Okay, so even if we have continued climate variability, we have probably in our future wet periods. Don't know how wet, don't know when, and don't know how long, so you can't forecast that part of it. We also have future droughts. So, we have drought periods later in the century based on decadal variability that, if we don't get temperatures sort of reined in, they occur under much, much warmer conditions. And so we already have trouble. We're seeing, if you're watching the Colorado River situation, is droughts are problematic, but when they're warm droughts, they tend to melt the snow and it doesn't make it into the springtime season and doesn't turn into runoff. So even a shift towards wetter conditions, if it's not snow and it's higher up in elevation, we have less water to deal with across the whole region. Okay, so my closing points here real quickly is we have complex hydroclimatic variability at weather timescales, dominates all of Arizona, leads to high levels of interannual variability. Variability. We know that. It's just watching in the summertime, it rains in your neighbor's house, doesn't rain on your house. Like, that's normal, and that's what we should expect. So climate models project similar, if not higher, variability in the future. Precipitation projections have much higher uncertainty. That's still not really getting better. There's a new set of models called CMIP6, and I've seen a little bit of stuff come out of them, and there's apparently some better constraints on some of this, but still a lot of questions, things it doesn't do well for the Southwest, so we kind of wait for that to get better. Temperatures are expected to warm dramatically in the century under high emission scenario. And then those higher temperatures decrease snowpack and increase levels of evapotranspiration. Shift towards increasing aridity. Can precip keep up? Probably not if temperatures continue to go up, right? I mean, that increasing level of aridity. So that's, part of our animus to mitigate greenhouse gases is for here especially, is to just rein those temperatures in so we don't have a huge shift in water balance in the future, even as we have wet periods going forward. Okay, and so real quickly too, Susie asked me to plug RainLog if anybody's interested or maybe is already participating. This is a program that I work with, and it's real simple backyard precipitation monitoring. We have a lot of observers in Tucson, and you never can have too many rain gauge observations because I was looking at this is actually from last summer. This little plot here is from June 15th through the end of September. You can see here is that in neighborhoods there were people seeing, 1.5 to 2 times what their neighbors were, and these data are becoming really, really useful. I did an analysis and wrote up a paper here, which is it's open access, and I can send you the link if you're interested in seeing what we came up with. We're just sort of looking at the variability of precipitation and trying to understand how to use the data. And then I just got a tool up this week where I'm using RainLog data and CocoRaws and the NOAA sites, as well as the flood control district gauges to track drought over these different timescales. And so that link is down here. And if you don't catch these, I can send you the presentation and certainly chat you the links too. So thank you. It was hopefully that was helpful, and I'd be happy to field any questions.
Okay, thank you so much, Mike. We really appreciate that, and gives us certainly a lot to chew on and worry about over our long summer. If anybody does have questions, feel free to enter them into the chat at this point. I'm sure Mike will be happy to answer them. And Susie, if you want to step in and facilitate our questions, you always do a fantastic job with that.
Okay. Thank you. I was muted. There were some questions in the chat about recording of the program, and I tried to respond to that, but I don't think my message went to everyone. But Jack, I was wondering if you can direct people on how to view the recordings in the YouTube? Is that actually in our Tucson chapter email website? Oh, you're muted.
Sorry, I don't know that we have a link to the YouTube on our website. We very well may. If you do go to youtube.com and look up Arizona Native Plant Society, there's a statewide
Okay.
chapter page, and then there's our local chapter page where we post videos. So it's just, you look up Arizona Native Plant Society, you will see the pages for the state and for our local chapter there. And we do have most, if not all, of the talks from the previous season.
Thank you. Since I've seen all the talks, I haven't been looking at those.
All right.
So, well, we had some comments too. And so this is another aspect, I guess, of when we do have good rains in the winter, the problems then with invasive plants, the stinknet and the buffalo grass, just comments that those have thrived in the wet winters. John Schuring mentioned that.
Yeah, absolutely.
In 2019. And then I don't see a lot of other questions. I think if at this point, if people would like to just unmute themselves and ask directly, that would be fine, or you can put it in the chat.
Question?
Go ahead.
Yeah. What is the role of the high pressure systems that would seem to defeat the buildup of clouds and moisture and rainfall? It looked like we had quite a few arrested cloud development. The high pressure systems of last year basically sucked up the moisture. It wasn't that there wasn't any moisture in the atmosphere, but cloud formation got defeated, and therefore we didn't have rainfall. How does that all play out?
Yeah, no, it's a great point, and I think you're on the money. So last summer, what ended up happening was, so if you're familiar with in the monsoon circulation, one of the key aspects is that we call it the four corners high pressure system. And so the high pressure system ideally is north of us, and it's over the four corners, and that puts us just slightly off of the high pressure system to the south of it, which is slightly cooler at higher altitudes, and it's also puts us in a deep easterly flow, and that's ideal for generating the instability in the atmosphere. When that four corners high drifts overhead, it's just like you said, you'll end up having something called an inversion in the atmosphere, and you may remember this, but we would end up having pancake clouds. And so you got a really hot atmosphere and even some moisture, but the clouds will hit the inversion and they'll sort of spread out. And if they don't have enough energy to poke through that inversion, they won't turn into storms. And we ended up having that situation because the whole four corners high system was sagging south. So northern Mexico ended up, they didn't have a great summer as well, but it was better than we were, and it was just across the border, just because that slight shift in the position of the high pressure.
Thank you.
Mm-hmm.
Okay. And then now actually we do have some more questions. Maybe I had missed those. One is, what is the address to find the upcoming climate model reports that you mentioned?
I can put them in chat. I got to find my chat window here. Just 1 second. I'll put it in chat here if somebody else wants to answer.
Okay, and then
Ask
also
another question.
The rain log address.
Yes, it's great. Thank you.
Okay. For some reason, when I tried to use the chat, I don't think my message was going out to everyone. So then I'll wait a minute to ask you the next one.
Sure, you can go ahead.
Oh, okay. Let's see. Oh, someone said, you mentioned types of moisture, rain and snow. How important is snowfall on Sky Island peaks to the water security of Tucson and southern Arizona?
Yeah, that's a good question that I'm out of my lane with that. My understanding, and this is, I'm just trying to recall talking with hydrology colleagues here, is that we do end up having water that can recharge the local basin. It's called mountain front recharge. And I do think I think it is important. That's all I can say. I don't know much more about it than that. I shouldn't even venture that far.
Well, and then as someone who works with farmers as an extension agent, what do you tell farmers in Arizona about the future?
Well,
I think they should start growing agaves myself, but.
Yeah, you know what? Well, I mean, farmers in Arizona there's a lot of different kinds of farmers. And so the ones in the lower Colorado River, you know, that's all vegetable crops, and they are largely vegetable crops, and they've got a lot of adaptations, and they will adjust really quickly based on water availability, but they have a lot of water because they have a lot of water rights. We also have an interesting phenomenon in the state where we have a lot of new orchard trees being planted, and that's a little bit more challenging because a lot of those orchard trees actually need chilling requirements to produce fruit. And you plant a tree now and it's got 20, 30 years to maturity. It may be too warm to actually have those trees fruit correctly. And that's not real well sorted out right now. So it's, you know, we're still kind of working on that part of the communication.
So, okay. And then what about, I guess in gardening, mulching to slow down evapotranspiration?
Yeah, that's what I do. I mean, I don't know. No expertise other than that's always been my strategy. I usually rock mulch cacti and wood chip mulch everything else. So I think there are other gardening. I mean, I'm not a great gardener, so there's probably others on the call who could attest to that.
And this one, okay, in 25 words or less. No, I'm just saying that. What factors drive or account for poor monsoon seasons?
Oh, 25 words or less. I'll try to do it in even less. It's the position of the high pressure.
Oh, that we were talking about before.
Yeah, that's key. There's a lot of other moving parts, but if that's not right, it's hard to do it well.
Okay. And Jack, do you see any more questions? I'm not confident that I'm seeing all the
questions. So there's one other one in there that I think was asked by Dan and answered. And Jerome Ward asked, are farmers changing crops due to future climate change and drought?
Yeah, I don't end up working with many row crop farmers, but they many of the crops, vegetables are slightly different, but anybody who's doing sort of row crops kind of related to grains, many of those crops are annuals, and you can end up, it's all genetics and seed. And so genetics with seed types is happening everywhere in the world related to climate. So, you know, they try to tune up the crop selection for the anticipation of what season they're going to get, and even the kind of the length of rotations. So there's a lot going on in agriculture because it's a big industry, a lot of science, and you know, a lot of money. So
gotcha.
Question?
Okay.
Yeah, go ahead.
Yeah. What do you see as the role of geothermal heat flux from irregular submarine volcanism in the extreme Southwest Pacific, the number of subduction zones and structures? What role does that have on influencing El Nino formation? What kind of studies have been done about heat flow in the Pacific to create this kind of erratic ENSO circulation?
Yeah, no, it's a good question. I don't know much about that, and I'll venture this is unfounded, but I don't think the volcanism, I don't think the energy flows are at a scale that's as big as the surface energy fluxes with the sun. And again, these are really different depths, because El Nino is occurring at it's basically the surface of the ocean. And so I don't know how to answer that much more than it is much more solar driven. And it's really, there's a really interesting study that came out just in the last couple of weeks that has, and we've known this, but El Nino, La Nina actually do have some synchrony with solar cycles. And there was this really interesting prediction that we would have a La Nina with this change in the solar cycle, and it worked. So you have all this sort of statistics that could just be curve fitting, but it was kind of interesting. And there's some science and modeling that suggests that there is this kind of weak forcing between solar variability. But I'm sorry, I don't know much about the volcanism part of
So
it.
you're suggesting that El Ninos and La Ninas are correlated with, maybe indirectly, with sunspots then?
They are, yeah. I mean, there are some studies. It's not the primary driver, but it has some synchrony with sunspot cycles. Yeah.
Awesome. And then we did have one more question pop up in the chat, and we'll try and get you out of here soon. But this is a good question. The position of the high pressure as prime driver of the monsoon. What determines the positioning of the summer high pressure cell?
Yeah, it's not super clear what does control it. And if we did know, we'd have better forecasts for the season. What can end up happening is that you can have an active jet stream north of the high pressure system, way off in the East Pacific, that can kind of beat it and nudge it around. And then we also know that the Atlantic Ocean and the tropics can actually come around and move the high pressure system around as well. So they're still kind of figuring out how the gears mesh together, but it's both upstream and downstream, north and south of the high pressure system.
Got you. Well, that looks like everything we have in the chat. I don't know if you see anything else, Susie, but thank you so much, Mike. That was a really awesome closer to this very interesting 2020-2021 Plant Society season. So thank you for that. And we'll all be hoping for rain, I guess.
That's right. Yeah, I wish everybody a happy monsoon, and thanks for having me.
All right. Have a great night. And
all right.
Have a great night, everybody else. If you have any questions, get in touch with the Native Plant Society email or check out our website. We'll have some fun updates coming soon.
Yeah, and thank you everyone for being here and for being supporting all of our programs that we've had through the year. It's been great. Okay, adios.
Have a great night, Susie.
Thank you. Bye-bye. Bye, all.